In this presentation, we're going to look at binary trees, and they're a little different from some of the other data structures we've looked at. In the images here, we have something we've seen before called a linked list. We have a pointer to the beginning of the linked list, and each node or element in the linked list has a pointer to the next element in the linked list. And we either have sentinel nodes, dummy sentinel nodes at the beginning and end, or we have a null pointer at the end of the list. There's different ways of implementing it. As we'll see later on in the course, we can make a more general data structure called a graph that's a collection of nodes and a collection of edges, and they can be connected in almost any way that you can imagine. A lot of different combinations. Before we get to graphs, we're going to look at a slight modification of a linked list or a special type of graph called a binary tree. And a binary tree structure is kind of like an inverted tree where we put the root at the top and we put the leaves at the bottom. So, and the name binary tree, as it suggests, means that each node has two child nodes. So every time we go one level deeper in the tree, we're doubling the capacity of storage in the tree. The topmost node is what they refer to as the root node. Any node in the tree that does not have any children is referred to as the leaf nodes. And if it's not a root node, and if it's not a leaf node, then refer to it as an internal node. So 1, 3, 4, 2, 5, and 6, they're all internal nodes. We can consider the height or the depth of the tree. So if we define an empty tree where the root node is null to have a depth of 0, then this particular tree would have a depth of 1, 2, 3, 4. So we'd have a depth of 4, or a height of 4 for this particular tree. A tree can be balanced or unbalanced. In this particular diagram, the tree is balanced, which means there's an equal number of nodes on the left and right side of the root node. So we say that this tree is balanced. As we'll see when we get into the programming, trees are naturally recursive, and so it can actually be easier to create tree functions or tree methods using recursion. Where is the recursion? If we consider this to be a root node and it has left and right children, notice that we could separate almost any of the other internal nodes from the tree, and we could consider the 2 to be the root node of the subtree. And so 2 looks just like 0 does in terms of it being a root node if this were separated from the rest of the tree. So each of the nodes has a left and right pointer as well as some data. So it's similar to a doubly linked list, except there's a parent-child relationship between the nodes rather than a left and right type relationship. One of the common operations that's done with binary trees is to traverse them. And we did this with linked list. We traversed the linked list looking for the largest thing, counting the number of items in the list, searching to see whether or not something was in the list or not, printing out the list. We can do something similar with binary trees, and we define several different traversals. Here they're called pre-order, in-order, and post-order. Let's look at the in-order traversal first. For the in-order traversal, we consider in the following order the left part of the tree, the current node that we're at, and the right part of the tree. So if we start at the root node, which is where these traversals start, we first want to consider the left part of the tree. So we go down to node B. At this node, we want to continue the in-order traversal or start the in-order traversal for this node. So we want to consider the left part of the tree. So at B, we start with left and we go down to node D. At node D, we want to consider or start at the left node. But node D's left node is null. Notice there's nothing coming out of node D, so its left and right are null. So at node D, the left is null, so we don't print anything. Then we consider the node itself, which is D, so we print D. And then we consider the right part of node D, which is null. So here we just get the D. So we've done the left part of B now, so now we're back to B. Now we do the node itself, which is B, so we get the B. And then we do the right part of B, which is null, so we don't do anything. So we've finished node B, now we're back up to node A. We've done the left part of A. Now we're doing node A itself, so we get the A. And now we're going to do the right part of A, or the right child of A. At node C, we're going to apply the in-order traversal again, which is left node right. So at node C, we apply left, or we go left, and we get to node E, and again we're going to apply left node right. Node E's left is null. Now we go to the node itself, which is the E, and node E's right is null. So we finish node E, we go back up to C. We've done C's left. Now we're going to do the node itself, which is C, and here we're going to do the right part of C. At node F, again we apply left node right. Left is null, node F itself is F, and right is null. And so we've done all of F, we come back to C, we've done all of C, left node right, we come back to A, we've done all of A, left node right, and so we're finished the traversal. And so this is the order of what they call the in-order traversal of a tree. Notice this particular binary search tree here. What would the in-order traversal of this be? So the in-order traversal of this particular tree here, we start with node that has a value of 15, and at each node we apply left node right. So at 15 we go left. At node 10 we apply left node right, so we go left. At node 8 we apply left node right. Left is null, node is 8, so we get an 8. And right is null. We get back up to the 10, we've done left, now we need to do node, which is 10. And now we do right. We get to the 12, we do left, which is null, we do node, which is 12, and we do right, which is null. So we finish this node, we go back up to 10, we've done left node right, we go back up to 15, we've done left, now we're ready to do node, which is 15, and now we do right. At 20 we do left node right, so we jump down to 16. At 16 we do left node right. Left is null, node is 16, right is null. We go back up to the 20, we've done the left part, now we need to do the node itself, which is 20, and now we traverse to the right part of 20. At 25 we need again to do left node right, the left is null, the node is 25, and the right is null. So we finish 25, we go back up to 20, we finish left node right for 20, we go back up to 15, we finish left node right for 15, and so we're finished with the traversal. In this particular case, notice what we've done is we've printed out all the numbers in order. So if the numbers are inserted, if the content of the binary tree is inserted in a particular order, and you do an in-order traversal, you'll get those values done in order. And so this is one of the benefits of a binary search tree. Here, the letters A, B, C, D, E, F, and so on have not been inserted in really any particular useful order. But here the numbers have been, the tree has been maintained so that all the numbers to the left of a node are less than or equal to that particular node's value. And so this actually allows us to create a binary search tree, and if, as you can imagine, every time we search down the tree, we're reducing the content that we're searching in half, and so this gives us a log n complexity or a log n performance. The pre-order traversals and the post-order traversals are similar. It's just that the order of left node right is changed. So in the pre-order traversal, you start with the node and then we go left and right. And in the post-order traversal, we do the left node, the right node, and then the node itself. And there can be different situations where you'd want to use different traversal orders. We'll see more of these in exercises in the course. How do we apply trees? What are the uses of trees? Well, the first use is actually to store things in a particular order or store things that can be searched for relatively quickly. So we can use them for a bag class or sets, or to store a list of data that we want to be able to access in order or access rather quickly. Something else that we can use trees for is for decision making or diagnostics. So if you've ever called a technical support line, it's not uncommon that they'll ask you a series of questions, and based on the answer, the questions that they may be asking you may be actually part of a script that go through a diagnosis type hierarchy. And so that's one possible use of trees. Another one is we can use trees for data encoding or compression. And one common trick for doing that is what they call a Huffman tree. And in a Huffman tree, we put characters in the tree based on their frequency. Now, this is not a realistic Huffman tree because E should be really high up on the tree because it has such a high frequency. The letter E, I think, is the most common letter used. So this is maybe not a realistic Huffman tree, but it still gives us an idea. What happens is, in the ASCII table, each character takes up 1 byte or 8 bits of storage. In this particular tree, every decision of the root or an internal node is made by a value of either 0 or 1. So the letter A can be encoded as 00. The letter D can be encoded as 110. So if you imagine, we could encode the word cab with a 1 and a 0. So 1 would mean go right and 0 mean goes left. So 1 and 0 would encode the C. And then for the A, we have a 00. And then for the letter B, we have a 01. If we were to store the letters CAB for the word cab, if we were to store that using the ASCII values, it would require 3 bytes or 24 bits of storage. Using this Huffman tree, this binary tree encoding, we can store the word cab with just 6 bits. So that's a significant compression ratio and another use of binary trees. In this presentation, we're not going to look at some code just yet, but we are going to go through some walkthroughs. In particular, I'd like to do a walkthrough of an insertion and a walkthrough of an in-order display. The code that I'm going to use is from this week's assignment. We can take a look at that briefly. Here is a header file that contains definitions for a tree node and a binary search tree. So the data for a tree node are whatever information we want to store, in this case integers, and pointers to the left and right tree node. Similar to the doubly linked list, except the left and right are going to be pointing to child nodes rather than left and right nodes. The binary search tree is going to contain a single pointer to a root node and then a collection of functions. The constructor will just set the root node to null. The isEmpty will just ask if the root node is null. And then the display may do an in-order traversal and display all the elements. The search may also do an in-order traversal looking for a particular target value and return a true or false. Adding to the tree will add an integer to the tree, and we'll see how that works in just a minute. Getting the minimum value, so this is searching for the minimum value in a tree. Again, we can do an in-order traversal and just keep track of the smallest value. You may be wondering, why are there duplicates of some of these functions? So in particular, why is there an add here that's private and an add here that's public? In order to do the recursive version, we need to be able to pass in a pointer to the subtree. And so that's what all these private functions do. They have a tree node pointer being passed in, which is a pointer to the subtree that we're considering on the recursive call. Some of those pointers are passed in by reference, meaning that we want to change them. So if we add in a new value, we may need to change what the pointer points to. So for example, if the root pointer is null, we want to change it to point to a new node that has this particular value that we're inserting or adding to the tree. When we're deallocating the memory for the tree, destroying or freeing up the memory for the tree, we're going to be deleting those pointers and setting them to null. So since we're changing those pointers, we want to pass them in by reference. The rest of these, display, search, and get minimum, we're not changing the values of the tree. We're not modifying the tree in any way, so we can pass in those pointers by value. So let's take a look at a code walkthrough. First we'll look at the insertion. So we'll look at how we add. If we go to the definition of add, all it does is call the private version of add, where we're inserting the new value x and passing in the root of the tree. So if we go to this version of add, the private version, you can see that we're passing in the new value of x to add and a reference to a tree node pointer. So what happens if P is null? If P is null, and then P could be the root node, then we allocate a new node, set its value, and set the left and right pointers to null. If P is not null, and we want to insert the values in order such that values on the left part of the tree are less than or equal to the values on the right part of the tree, then we just do a comparison of x with the value at P, the data at the current node P. And if the value we want to insert is less than or equal to, we're going to recursively add that value to the left subtree. If it's not less than or equal to, then we just add that value to the right subtree. And as we walk down the tree, move down to the left or move down to the right, eventually we'll find a place where we have a null left or a null right, and then when that p becomes null, that's where we'll insert the new value. Again, let's do a walkthrough and see how this might work. Here is the add function. And here's some values that we want to add to the tree. And here's the tree root, which I've left empty to indicate that it's currently null. So that's the case after we've invoked the constructor. Maybe this is in main for this tree variable. The first value we're going to add is a 5. So and this add is going to call this version of add that takes two parameters, the value 5 and the root node to start off with. So p is going to be the root node. If p is equal to null, and that is the case, then we're going to allocate a new node. So we've allocated a new node. We're going to set its value to the new value, which was 5. And p is going to point to it, to the new node. So that was done here. P equals new tree node. So p, which is the root currently, is going to point to the new tree node. And the left and right pointers are null, so there's nothing coming out of this particular node. So that's the first add. The next one we're going to add the 3. And again, the public version of add calls this private version of add with 3 being passed in for x and the root node being passed in for p. And we ask the question, is p equal null? No, the root node is not null, it's pointing to something. So we do the else part. Is x less than p info? Well, x in this case is the 3. This is the one we're working on now. And p left, which is p info is currently 5. So is 3 less than 5? And the answer is yes. And so we're going to add the 3 at p left, which is root left. So we're going to be adding here onto root left. I'll go ahead and draw the arrow in, but keep in mind that it's null right now. So when I do the recursive call, I get a 3, and p now is root left. So is p null? Yes, it's not pointing to anything right now. So we're going to make a new tree node. And we're going to set it equal to p. And we're going to set its value of 3. And that's it. We're finished with that. So we finished with this version of the function, we finished with this recursive call, and we've jumped back. So now let's look at adding the 7. And when we go to add the 7, we start off with p being the root node, x being 7. Is p null? No, it's not null. Is x less than p info? No, 7 is not less than or equal to p info, it's greater than. So now we're going to add x at p right. So p right, I'll draw it in here, is null. It's not pointing to anything, but I'll draw an arrow not pointing to anything. We know it's null. So we're going to make this recursive call with the 7 and p right. So we're back up into recursive call, and p is now this pointer here. Is p null? Yes, p is null. So what we're going to do then is allocate a new node, and we're going to set it equal to p and put the value in there, which is 7. Well, it already has the value 7 there. So now we're ready to do this one, where we're going to add the 6 in here. And I think I need to spread my nose out a little more. Give me some space. Alright. So now we're ready to add the 6. And so we call this function where p is the root and x is 6. And we ask if p is equal to null, and the root is not null. So now we want to know if x is less than p info, and that's not true. X is greater than p info, so we're going to be adding the 6 to p right. So now when we make this recursive call, x is still 6, but p is now the node that points to 7. So we ask the question, is p null? And the answer is no, so we go to the else part, and is x less than p info? P info is now 7, x is still 6, so this is true, so we're going to be adding x to the left of p, and remember that p is 7, so we're going to be adding to 7's left, which is null. So we jump up to add here, we're adding the 6, we're adding to p, which is now 7's left, and so that's null, so we need to get a new tree node. Set it to p, which was 7's left, and change its value to, set the value to 6. And so that adds in the 6. The last one we're going to add in is the 4. We call this function from the public version with the 4 for x and the root node for p, and we ask if p is null. No, p points to the 5, so it's not null. And we ask if x, which is the 4, is less than p info, which is 5, so that's true. So we're going to be adding the 4 to 5's left. So we go to the recursive call, we're adding the 4 to 5's left. Is p null? Is 5's left pointer null? No, it's not. It's pointing to the 3. So then we say, if x is less than p info, is the 4 less than p info? No, it's not. It's greater than. So that means we want to add the 4 to p's right. Well, p's right isn't shown in the diagram, so I'm going to draw it in here, and just keep in mind that it's null, it's not pointing at anything. We make the recursive call, x is still 4, and p is now the right node, or the right pointer of 3. Is p null? Yes, p is not pointing anything, so it's null. So we're going to make a new node, make p point to that new node, set its value to the 4, and set its left and right pointers to null. So we've finished adding all the values in, and that's what our binary tree looks like. You can see that this particular binary tree is not full, meaning there's room to add another node here, and there's room to add another node here. And if we consider the root node, it is balanced in that we have 2 nodes to the right of 5 and 2 nodes to the, 2 nodes to the left of 5 and 2 nodes to the right of 5. So this is how we would trace through or step through the insertion of a few nodes to a binary tree. The next thing we want to look at is an in-order traversal. We'll actually try to look at the function call stack. So here's a tree that we saw before. How can we trace the in-order traversal? In main, the tree would have been set up so that the tree's root node points to A, and we're going to call this in-order traversal function, and maybe we should look at that. The display is the public version, and it calls the in-order traversal function, passing in the root node, and then just prints out a return. So if we look at the in-order display or the in-order traversal function, it's the private version that is recursive. And it simply asks the question, is p not equal to null? And if that's true, if it's not empty, then we do the in-order display on the left. We print out the value at this particular node and the in-order display of the right. And this is familiar to us from what we saw before. The in-order traversal is left node right. So we're considering the left part of the tree, the current node, and then the right part of the tree. So let's see if we can do a traversal here. So the first call will call from the public version of the display, we'll call the in-order display of tree root. And in this particular case, we're calling not main, but the in-order display where P points to A. And this particular call says to do this, the in-order display of P left. I can just copy and paste this, I guess. Maybe it didn't work out so well. So this is going to be the in-order display of P left. Print P info, P's information, and then the in-order display of P right. So before we get to the print part, we have to push onto the call stack the in-order display of P left. So we're going to get another version of this on top of the call stack. And in this particular version, from here, P points to A. When I do the recursive call P left, that's going to be the P that points, the pointer pointing to B, because the left of A is B. So this is going to be pointing to B. And then we're going to do the in-order display of P left. So we're going to get another version of this on top of the call stack. And notice we haven't actually printed out anything yet. We started with main, in which the tree root points to A. We called the in-order display passing in the tree root. We're here in the in-order display where P points to A. We're making a recursive call, so we have to put another of these stack frames on top. And in that recursive call, we want P left. Well, the left of the pointer to A is a pointer to B, so we get a pointer to B. We make another recursive call, which puts another stack frame on top. And the left of the pointer that points to B is a pointer to D, so we have to replace the B with the D. And now we make another in-order display call here. So we need another stack frame. And in this particular stack frame, where P points to D, the in-order display of P left, D's left is null. So now this is a null. And the code actually has an if statement that says if P is not equal to null. Well, in this case, P is null, so we actually don't do anything, we just return. So then this, since it just returns, gets knocked off the call stack, and I'll put it over here because we'll need it again. Now we're back to this stack frame And the last thing we did was do the in-order display of D's left. There was nothing there, so we didn't do anything. And now we're ready to print out our first value, which is P points to D. We print out D's information, so the first output is D. After we've printed out the D, then we're going to do an in-order display of D's right. Well, D's right is null, so we get this stack frame back on top, where P points to null. Not the null on the left of D, but in this case the null on the right of D. Same value, but a different pointer, stored at a different pointer. The code says ask if P is not null. Well, P is null, so we're done. This gets popped off the stack frame. We're back here, and what we just did was tried to print out the in-order display of D's right, and there was nothing there, so we didn't do anything. So now we're actually finished with this stack frame, and we can pop it off. We're back to here. We've done the in-order display of P left. Now we're ready to print out P, and in this particular case P was pointing to B, so in our output we get a B. Now we're ready to do the in-order display of B's right. Well, B's right is null, so we get this pushed on top of the stack. P points to null, which is B's right. The code says if P is not equal to null, do something, but if P is equal to null, we don't do anything. So this again gets popped off the stack. We've done the in-order display of B. We've printed out the B. We've done the in-order display to B's right. So we've finished all this code, so we can pop it off the stack. Here we have done the in-order display of A left. So now we're ready to print P's info, and P is pointing to A, so we get an A. And now we're going to do the in-order display of P right. Well, P right points to the C, so we're going to push another stack frame on top where the pointer points to C. We're going to do an in-order display of C's left, which is the E, so we're going to get another copy of the stack frame, and C's left is E. And now we want to make another recursive call to E's left. E's left is null, so we get this version of the stack frame where P is null. Since P is null, we don't do anything, so this gets popped off the stack frame. And we've done E's left. Now we're ready to do E's information, print out E's information, which is E. And now we're ready to do E's right, the in-order display of E's right. E's right is null, so again we get this stack frame put on top. E's right is null, null gets passed in for P. We don't have to do anything, so this gets popped off the stack. And now we've done E's right, so we've done all the code for this one, so we can pop it off the stack. We've done C left. Now we need to do C itself, which is to print it out. And then we want to do the in-order display of C's right. Well, C's right is F, so we're going to make another version of this stack frame. And in this case, we're passing in C's right, which is a pointer to F. And now we're ready to do an in-order display of F's left, which is null, so we get this stack frame on top. There's nothing to do, so we pop it off. Now we print out P's information, and that is the F. And now we do the in-order display of P's right, which is the right pointer for F, which is a null. Again, we get this stack frame where P is null. There's nothing to do, so this gets popped off. We finish F's write call, so this gets popped off the stack frame. We've done the in order display of C's write, so we're finished with all this code, so that gets popped off the stack frame. We've done all the in order display of A's write, so that's done, so this gets popped off the stack frame. We've done the in order display of root, so we're finished with main, and that ends our program. And our output for the in order traversal is DBAEFC, which is not in alphabetical order because this tree wasn't really created that way. There's no left-right order for this particular tree. But this is an example, a couple examples of tracing through some of these recursive function calls, showing how we insert values in order into a binary tree and then do an in-order traversal of data in a binary tree. In other presentations we'll actually look at some code. We'll write some new code for some other binary tree functionality. Let me know if you have any questions on this.